All right, here we go with buffers. Everybody's most hated topic on the AP chemistry exam. Oh, helps if I turn the thing on first. All right, so a buffer is all about, I think I'm going to do this one first. A buffer is just a solution that is capable of resisting changes in pH whenever you add an acid or base to it. Strong acid, strong base, doesn't matter. As long as it's just a little bit, it's not going to change its pH very much. And a buffer solution always consists of a mixture of a weak acid and its conjugate base, or if you wanted to say a weak base and its conjugate acid, but it's kind of the same thing because the conjugate base of any weak acid is also a weak base. So just a weak acid, weak base combo. And the reason that it works is because you have this acid that can neutralize a little bit of base, and you have a base that can neutralize a little bit of acid. So how do you do it? Well, it's called the common ion effect, and I need to draw in my little double arrows. Basically, what happens is if you have, say, this reaction right here, this is just the ionization of acetic acid, and if you were to add a salt that contained this ion, such as sodium acetate, then this particular reaction is going to be affected according to Le Chatelier's. You add some of this ion here and it's going to cause it to shift back towards the reactants. Now the reason I say that this acetate ion is going to come from this is because sodium acetate will completely ionize into the neutral sodium ion, which we're not really concerned with because sodium's not in here anymore, and that acetate ion, which we are concerned with because it's right here in our equation. And the resulting solution of this is a buffer because here we have a weak acid and here we have the conjugate base of that weak acid. So looking at this, to make a buffer solution, what weak acid must be added to some amount of sodium acetate? So we have this salt. We want to make a buffer solution. So what do we add to this? And then they want us to write the chemical reaction and its equilibrium expression. Well, we look at this and we go, okay, what ions do we have? We have sodium, we have acetate. Sodium is the neutral ion of a strong base, so it's not going to be a part of any buffer solution. But of course, the acetate ion, like I just said, is the conjugate base of a weak acid. So add in some acetic acid, the CH3COOH, and writing the chemical reaction. This will ionize a little bit into the hydrogen ion and that acetate ion. And the corresponding equilibrium expression, Ka, is equal to reactants, H plus, CH3COO minus, divided by, sorry, I don't know if I said reactants or products, but it's products that go up here, and reactants go on the bottom. All right, understanding acid-base reactions. You've got 4 situations that you could have. And this is making the assumption that we have equal volumes and equal molar. We'll get to what happens if you don't have this situation in a second. But this is saying, we have 1 liter of 1 molar each of these solutions. So if you have strong acid plus a strong base, then you're going to end up with a neutral salt. NS stands for neutral salt plus water. And here's an example. And the second equation here is taking this complete equation and breaking it down into the net ionic. If you remember, strong acids and strong bases completely ionize, and salts completely ionize, so those ions are going to end up canceling out as spectator ions, and this is what you're left with. The reason that the solution is normal is because both the acid and base ions are neutral ions, which makes the whole thing neutral. They cancel each other out. If you had a strong acid plus a weak base, then you're going to end up with a weak acid and some kind of neutral compound, whether this neutral compound is a neutral salt or maybe it's just water, but it's just some kind of a neutral compound. So here's the example. Strong acid in this case is HCl. Weak base in this case is the NaC sodium acetate that we had on the last slide. The reason that this is a weak base, remember sodium is a neutral ion, but the acetate ion is just ever so slightly basic. And we are going to make sodium chloride, right here, neutral compound, and acetic acid, a weak acid. If we cancel out our spectator ions, the sodium and the chlorine again, spectator ions here, and we end up with kind of the reverse ionization of the acetic acid, and the resulting solution is in fact slightly acidic because we have a weak base, but a weak acid that is stronger than the weak base, and so weakly acidic. If we have a strong base plus a weak acid, we have basically the exact opposite situation here. Instead of ending up with a weak acid, we end up with a weak base, and then that neutral compound. Example I have here is the strong base, sodium hydroxide, and the weak acid, acetic acid. You're going to make sodium acetate plus the neutral compound water. Crossing out our spectator ions, looks like sodium's the only spectator ion we got here. So you end up with the hydroxide ion reacting with the vinegar, and you get the acetate ion, which is slightly basic, and the neutral compound. And then if you had equal volumes of equimolar weak acid, weak base, you're not going to get a whole lot of a reaction because neither one of these guys really wants to ionize much. They're perfectly happy staying as they are. So, right and balanced complete and net ionic equations for the reaction of ammonia solution with nitric acid. Well, if you remember, ammonia has the formula NH3 plus the nitric acid HNO3. And this is going to react. Looking at this, you can say, okay, well, this hydrogen is going to be donated to the base, the NH3, which would then become the ammonium ion, and all that we're going to have left is the nitrate ion. Well, these two guys just end up coming together to make ammonium nitrate, the soluble salt. So then it asked for net ionic equation. Well, the ammonia doesn't really ionize much because it is a weak base, so leave that as it is. The nitric acid will in fact ionize, so you get hydrogen and the nitrate. And our product, the ammonium nitrate, is a soluble salt, so it will also ionize. And then you look at this and go, okay, what can I cross out? Well, I've got a nitrate ion on both sides, so they're gone, which leaves me with ammonia plus hydrogen ion, gives me the ammonium polyatomic ion. Now, chances are, once you get good at these, you can kind of look at this, and every time you see a nitrate, you just know that guy's gonna go, because it is the anion of a strong acid, which means it will ionize, and anytime nitrate is the anion in a salt, in an ionic compound, it's going to ionize, it's going to dissociate, it's going to dissolve, whatever you want to call that. And so up here, you could have crossed out the nitrates and realized that, skipping this whole middleman right here. When you're taking the AP exam, anything that saves you time is a good thing. Moving on, calculating the pH of a buffer. You calculate the pH of a buffer solution the exact same way you calculate the pH of a weak acid or a weak base solution using rice. So, starting with our question here, what is the pH of an aqueous mixture containing 0.2 molar acetic acid and 0.1 molar sodium acetate? So, the ionization that we're dealing with is the acetic acid, because this sodium acetate is really just a nice way of saying you have some acetate ion. So the acetic acid, CH3COOH, ionizing into the hydrogen ion and the acetate ion. So here's R. Now our initials. The initial is what you're always given in the question. So the initial, in this case, we have 0.2 molar acetic acid. We don't have any hydrogens to start out with, but we do have some acetate ions to start out with from our little salt right here. So our initial concentration of the acetate is actually 0.1 molar. And then our change is going to be minus X, and plus X. And the equilibrium concentration, remember X, when it comes to weak acids and weak bases, the change in this concentration is going to be so small that you might as well say, well, it's just 0.2. This, anything compared to 0 is a big change, so we're going to have the X there. And then 0.1 plus X, X, okay, keep in mind the Ka for acetic acid is 1.8 times 10 to the negative 5. This means it's 0.000018. This change right here is going to be similar, close to this number. If we took 0.2 and subtracted 0.000018, we're going to get like 0.19998, which might as well be 0.2. Same thing here. If we did 0.1 plus x, we'd have 0.1000018, which might as well just be 0.1. So just to save you from having to go through the complications of using the quadratic formula, that whole, I don't even remember it anymore. It was like a square root 4a minus 4a, I don't remember. Well, that's bad, I don't remember the quadratic formula. But instead of having to go through using all of that, just go ahead and make your estimation. It's okay in the grand scheme of things. Chemists use sig figs to keep the math easy on us. Even though I'm sure when you first learned sig figs, you thought it was the worst thing ever. So to find the hydrogen concentration, which we can then use to calculate the pH, you say, okay, Ka is equal to hydrogen ion times acetate ion divided by the acid. Plug in what we know. So 1.8 times 10 to the negative 5 equals x times 0.1 divided by 0.2. Well, these guys reduce down to 1 over 2 basically. So we have x divided by 2 equals 1.8 times 10 to the negative 5. I'll simply plug that into the calculator to find x, and you get x equals 3.6 times 10 to the negative 5. And then you just take the pH of that. So to find the pH equals negative log of hydrogen ion concentration. So in this case, 3.6 times 10 to the negative 5. So negative log 3.6 times 10 to the negative 5 equals. And we end up with a pH of 4.44. And so that's the pH of our lovely little buffer solution here. Now there are some tricks that you can use. Instead of having to go through all that we just went through with the rice table and doing all that extra work, there are actually some formulas, and these formulas are on your formula chart for the AP exam. First of all, the Ka of any buffer solution is X, where, oh, sorry, I put it right down here. X is equal to the hydrogen ion concentration times the concentration of whatever base you're dealing with divided by the concentration of whatever acid you're dealing with. So this is either going to be base and conjugate acid or acid and conjugate base. And then if you wanted to figure out the pH of a buffer solution, just take the pKa and add the log of the base over the acid, and you'll get right where you need to be. So it would save you all that work and having to divide it up into two separate parts and yada, yada, yada. So know these formulas, know how to use these formulas. And keep in mind, though, it's only okay to use these formulas when you are dealing with buffers. You have to recognize that you are dealing with a buffer. If you don't do that, then, well, you're just going to be lost. So this is kind of a summary of everything that we have been doing with acids and bases and equilibrium, Kas, Kbs, and then now buffers. So this is literally just a reiteration of all of it. So the strong acid, the X, remember X is equal to the hydrogen ion concentration, is equal to I, where I is just whatever the initial acid concentration is. And the reason that this works is because strong acids completely ionize. And so whatever the concentration is of the strong acid, that's going to be the concentration of your hydrogen ions. Same with strong bases. Whatever the concentration of your base is going to be, that's going to be the same as the concentration of your hydroxide ion. A little bit of a difference if you have a dibasic base like magnesium hydroxide, MgOH2. Well, you're going to get 2 hydroxides for every one of those, and so you have to take Y equals 2 times the initial base concentration. These came from our acid-base equilibrium notes, where Ka equals x squared over I. X squared correlates to the fact that your hydrogen ion concentration and your conjugate base concentration are going to be the same once you reach equilibrium, and this initial concentration isn't really going to change that much when you're dealing with a weak acid or a weak base. And now we've added in the whole buffer thing. So just keep all these straight and know, if you're dealing with a strong acid, strong base, you're up here in this part of the table. If you're dealing with just a weak acid or just a weak base, you're here. And if you have one of the buffer questions, you're dealing with down here. And I think I'm going to go ahead and split this into, I'll go ahead and do this one and then get into the examples. How do you know if you're dealing with a buffer? Well, you know that you're dealing with a buffer in these situations right here. And depending on what is excess determines whether or not you have a buffer. So if you have a strong acid plus a strong base and the base is excess, then the resulting solution is a strong base. If the acid is in excess, the resulting solution is a strong acid. And if they're both present in equal amounts, you end up with that neutral solution. This is kind of from that last slide that I was showing y'all, 4 slides ago. The one with all the words on it. This is what's new. So here, if we have a strong acid plus a weak base, and you have an excess of the base, then you get a buffer. Flip side of that, if you have a weak acid plus a strong base, and the acid is in excess, then you get an acidic buffer. This would be a basic buffer. This would be an acidic buffer. Then if you have weak acid, weak base, you'll always get a buffer. If the base is in excess, then you have a basic buffer. I'm going to clarify that a little bit. If the acid is in excess, then you have an acidic buffer. And if neither of them is in excess, then it just depends on whether or not the weak acid is stronger than the weak base. I know that's kind of confusing to say that, but it's whichever one of these two guys has the higher respective K value tells you whether it will be an acidic or a basic buffer. So buffer solutions are made in these situations only. This is when you know to use the buffer formula right here. Okay, so I'm going to go ahead and call this one quits, and we'll have part 2 just be all of the example problems.